Hello, you know that this week we will be talking about numerical optimization, but before that I want to show you how we can plot 2D graphs, and you know that 2D graphs means that we have multi-variable functions, two variable functions. Instead of y equals f of x, we have a function z equals f of xy, and how we can plot that. And let's see on an example. Let's say that we have a function, we have a function f of xy equals x times sine xy, okay? And we would like to see the graph of this function when x is between 0 to 5 and y is between pi to 2 pi. How can we do that? So the way is very similar what we did for plotting. First, we need to define the function. With an inline command, you can define your function x times sine xy, and you know that we are doing element-wise multiplication. And our function depends on x and y. I am pointing out this one inside the inline function. And after that, I need to open a mesh grid. Mesh grid is kind of a matrix. It will continue the information for the x and y axis. So for x axis, we will plot it from 0 to 5, and I have to divide this one into smaller regions just as we were defining x. So the increment is 0.1 for that. And for the y-axis, I'm defining from pi to 2 pi, and the increment is 0.01 times pi increment in each step it will go. So once we do that, we need to plug then inside this one into f, just as we were doing for plotting, if you remember it. So z equals f of x and y. The grid that we opened, we are plugged in this x and y inside our f. So right now our function turns back to a data. Okay? And the plotting command for the 2D plots are mesh command. Mesh xyz, or you can use surf command. Okay? Both of them is working. So once you do that, you will see the graph of sine xy times x, like that. And in MATLAB, you can even turn this, rotate this, and you can check the graph from different points, okay, from different angles. And in this part, the mesh grid command is important. So mesh grid commands, the first one is having the information of x, and the other one is having the information of the y value. And you are plotting this x and y value, this space, onto the z function, and you are plotting that in like that. And I can show this one in MATLAB to you. Let me copy paste this one. Actually, I have it, I think. 2D plotting, yeah, that one. See, I define my G function, XY grid, mesh grid. I open that, Z, and if you say run, I will share this one to you, and you can see the graph, and you can just by holding it and turning in different angles, you can see the graph from the different angles. This is your 3D plotting, okay? And what else we have? Now we can start numerical optimization. Why did I show this one to you? Because this is the kind of the first step for the numerical optimization. You can see your minimum and maximum of your function easily. In this numerical optimization, I started with an example. Let's see the two-dimensional wave equation. It's generally used in mechanical engineering to model vibrations in rectangular plates like that. And if the plates have all four edges clamped and sinusoidal vibrations is described with a double Fourier series, this is what you will see. And let's say that you have a certain instant of time, the height, z equals f of xy, over the point xy is given with this z function. As you can see, this is also two variable function, and we just talked about how we can plot it. So we need to define this one with an inline function, and by just defining the mesh, and after that you can mesh grid, and after that with the mesh command or surf command, you can easily plot this function. And this is gonna give the contour function, is gonna give you the contour of this one, or you can easily check, rotate it, and see your maximums and minimums. You can see that here, where are the points of maximum deflection? Here you can see that there are two maximums and there are two minimum points. And you can see where, not maybe clearly, but you will have an idea at least. And by just checking that, you can see that the minimums are appearing in 0.8 and at 2.5, maximums are occurring at 0.9 and 2.39 in this one. And we can easily solve this one with the calculus. You know it already, but before that I also plotted this one for you with the mesh command and contour command. So I define my function with an inline. I define my mesh grid from 0 to 0 to pi, 0 to pi, both of it is 0 to pi. And z is gxy, we plugged in this xy inside our function. And it's the first function, I plot the mesh xyz. You can see there are two maximums, local maximums, two local minimums here. And with the contour command, you can see that the local maximums and minimums, okay? How many extremum points you will have inside this function with the given boundary. And before that, this is gonna be given to you with the 2D plotting tool. In this one, if you run it, you will see the contour and the graph of f. You can see the contour a little bit in here. You can see the maximums and minimums. See, the yellow ones are maximums, blue ones are minimums. Okay? These are the local extremum points, and you can play with your graph like that. And this is the mesh one. Okay? So, yes, it is in here. You can check that. I will send these MATLAB's code to you. And these are first derivative test, second derivative test for the local maximum minimums. You know that. According to the first derivative test from calculus 1, if the first derivative is less than 0 and is at AP, and the first derivative is bigger than 0, so if the first derivative changes at the point P, then you will understand that FP is the local minimum, right? It's changing the direction. And if it appears inverse, like if the first derivative is positive and it turns to negative at P, then you can understand that FP is the local maximum. And the second derivative test, this time you are looking for the second derivative by checking the first derivative equals 0. This is going to give you the critical point if you remember it from the calculus. And at the critical points, if you are checking the second derivative test, and if second derivative is positive, then it's a local minimum. If it is negative, it's a local maximum. If it is 0, then you cannot get any conclusion from this second derivative test. You need to try to understand in different ways. Okay? And this is just one example for you. Find this, use the second derivative test to classify the local extrema of this function, x cubed plus x squared minus x plus 1. And in the interval is minus 2, 2. So with this kind of functions, the first step is always plotting. If you can do that, you can understand what kind of function you have. You know how to plot 2D, right? 1D. You are defining your function. This time I define with an x at x command, x cubed plus x squared minus x plus 1. And x is given minus 2 to 2. You are plugging x into f, y equals f of x. Plot x, y, r, so that you can compare 2D and 1D plotting easily, and these are very similar, you can see that. And here you go, this is your function. You can see that there's a local maximum, there's a local minimum here. Okay, so we know how to find it exactly. Take the first derivative, 3x squared plus 2x minus 1, make it equal to 0. The critical points are 1 over 3 minus 1. And take the second derivative. Second derivative is what? 6x plus 2, right? And plugged in inside the second derivative 1 over 3. It's positive, so it is a local minimum, which means that here it is 1 over 3. And checked at x1, another critical point. It was 1 over 3 and minus 1. We found that 1 over 3 is going to give us the local minimum. If I plug the minus 1 inside the second derivative, what do we find? It is minus 4, which is less than 0. It will give us this local maximum point. It is minus 1, and if you plug the minus 1 in this f function, you can find the y for that. Okay? This is just very familiar example for you. That's why I'm passing quickly. And also a second partial derivative test, if you remember it. If you have a function that depends on more than one variable, now you are looking for the critical points for f of x is 0, f of y is 0, which means that you are taking the partial derivative of f with respect to x0, partial derivative of f with respect to y equals 0, and you will solve them together, find the critical points. Once you find the critical points, what you are doing for the second partial derivative test, you are checking fxx, fyy minus fxy square. If that's positive, and if fxx is also positive, then your critical point is local minimum. If that is positive, but your fxx is negative, then you have a local maximum point. If that's less than 0, then fxy does not have any local extremum at PQ, so it's just a normal point. And if this is 0, then you cannot say anything according to this test. Okay? Remember, this is from the calculus 2, we already covered that. And this is just one example. Here you go. This time our function is 2-variable function. So to be able to plot it, again, I'm using the mesh grid. So this function, I just plotted from 0 to 5, 0 to 5. And if you check that, this is what you will get. And you will see that there is only one local minimum here. And to find that, we are taking the first derivatives to be able to find the critical points. These are the first derivative with respect to x, with first derivative with respect to y, partial derivatives. And if we solve this one together, what you can do, you can multiply the second equation by 2, add them, and you will find the only critical point is 3, 2. And we can see here this critical point is minimum, but let's check with the second partial derivative test. The second derivative with respect to x is 2. Second derivative with respect to y is fyy, again 2. And fxy, the derivative of this function with respect to y is minus 1. So we are checking fxx, fyy minus fxy square, which is positive. If that's positive and if xx is positive, which means that 3, 2 is a local minimum. Okay, it's the first case scenario according to the second partial derivative test. Okay, and again, for these kind of critical points and optimizations, you can do the plotting and you can see what kind of function you have. And what are those functions in general mean? So in general, we call them an objective function. We are trying to maximize or minimize this function. Sometimes this function only maximizing or minimizing is enough. Sometimes you need to maximize or minimize this function according to some constraints, okay? For example, let's say we have an electronics company. They are manufacturing several different types of circuit boards. And each circuit board must pass through several different departments. What kind of departments? Like drilling, pick and place, testing departments before they are shipping these products. And the time required for each circuit board to pass through the various departments is also known. So it has to stay drilling, 2 minutes, pick and place 5 minutes. These are known. And there is also a minimum production quantity per month that the company must produce. So the company must produce at least that much product. Let's say this is your aim, right? However, the company is capable of producing more than the minimum production requirement for each type of circuit board each month. And the profit the company will make on each circuit board it produces is known. So you know the profit for each circuit board. And the problem is determine the production amount of each type of circuit board per month that will result in the maximum profit. Of course, each company's aim is having the maximum profit. What does it mean? It means that you are trying to maximize your profit function, f function. So you will have a function. But in this function, the variables are also have some restrictions on them. And these are the constraints. And this kind of problem sometimes you need to solve, and this is also one way of optimization. Again, for most of the optimization problems, the objective function can depend on several variables, and you know how to check them. And one of the optimization methods we will talk in this one is the unconstrained optimization, the steepest descent method. I will talk it a little bit later.